Hi everyone, in this third part of the getting started tutorial for the GeoAR application, we'll go through the scripts that you have here in the scripts folder inside the assets and talk a little bit about the game objects that you have here in your scene and how try to provide you hints on how everything's connected. Quick reminder, the paper that explained the technology is published in the International Journal of Geographic-Information Science. Please don't forget to read it, especially here when you explain the system architecture. Have this very simple diagram that explains the main components, and here detail that you have basically two main scripts here. One to manage the calibration that calculated the transformation parameters in order to transform the geographic coordinates into the local coordinate system of the AR device, so that the visualization manager can load and transform the coordinates and display them accordingly. And they are supported by 3 DLLs that you implemented here. One is only about converting from geographic coordinates to project coordinates and vice versa. The other one's just responsible to provide the means to do the helmet transformation that calculated the parameters, and the other DLL is responsible for requesting the position of the users from the smartphone, which needs to run the Geo for HoloLens app that will be available here or in the Play Store from Android. So please read this first so that you can have an initial idea of this explanation. Okay, so in the second tutorial, the previous one, we explain a little bit how is the user interface and the interactions with the menu. And now the idea is to explain the scripts here, right? So I have here the initial menu, and let's start what's the aim of this application. In the resource folder, you have a file called scene1. That's just an example. So this is basic GML file, so XML file that provides the coordinates of some points coordinates here. Nah? So we have two churches, Stephansdom and Karlskirche, on this place, and you have their coordinates here, right? The geographic coordinates. And they want to display like a cuboid, a long rectangular feature that should be 120 meters high, and the sides should be 5 meters, right? And they provide as well information should be the height. You have this information for your terrain model, where they are placed, so that they can place on the ground, right? Other options that you can place that relative to the user height, then you set this value here. And the system what they need to do first, you need to do the geographic calibration in order to calculate the parameters that you transform these coordinates to the correct local coordinate system, so that they can be displayed at the correct position. Here are the position that you're gonna read, right? So remember here, you test later this application outdoors, and I have here coordinates from church that you have close by here from our campus. Of course, when you are using it, you need to have features that you have there. Another alternative is that you can load this information from a web server, but that you need to develop yourself. Therefore, you will stick to read this information from internal files that should be stored here in the resources. Okay. If you remember from the previous slide, I run here the application, the game mode. First thing that you need to do is calibrate, right? There is this button here, calibrate, and they will create the 4 calibration spheres where are the points that you can collect the position of the users, and they will be used to calculate the parameters. And this, in order to do the calibration as a user, you need to walk towards this place, and then if you have are properly connected to the application GPS for HoloLens, you started collecting the points. Right, once this is collected, you can click on the button to, when you have the calibration done, you can click the button to load the visualization, and then it's gonna load this file and transform the coordinates to the local coordinates. And here you have the option as well, the calibration options. I will restart this calibration to do indoor debug. In this case, if I click calibrate, you generate fake coordinates for the calibration point, so you can have a calibration in order to test it here or indoors. In case you don't have GPS, you can test the application, right? So, and then if you load, you can see the 2 rectangles there, one here, the other one there, and they are placed supposed they have the coordinates transformed according to the calculated parameters. Here are these 2, the Stefan's noms and the Karlskirchen, the game objects, and you can see here the calculated position after the transformation. Alright, let me reset this thing here. Okay, let's have a look here on this first thing here. This first game object here, UI, are everything that are related to the menus and user interface. Initially, the only one visible here is the main menu, but you have the others, panels and menu here, right? I already explained this in the previous thing. But you have here the main menu, and you can access the buttons here, the buttons collections. If you want to learn more about those kind of menu, please do the Microsoft tutorials, mixed reality tutorials, and they're gonna give you a good hint on how to implement those things. But here you have the button calibrate. What happens when you click this button? So you have the inspector of this game object here, where you have some their components. And one of these components are here, events. And then you have an on-click event. And then here you basically can set the behavior once a user click this event, and one of them is the calibration manager will run the function, the method calibrate. So what's this calibration manager? Note that if I click here, they're gonna highlight this game object. But what's this game object here? It's basically a game object that has no geometry, and it has a script associated to it. It's the calibration manager script. This is the calibration manager that is that you have there in the architecture, right? So once you click the calibration, let's go back here, button calibrate, it will run, execute the method of this script that's called calibrate. How can you find this easily? You go to script and find here the calibration manager, as you can see here, right? Let's open. Here is the calibration manager. This is the most complex and long script of this program because there is many things to manage here in this calibration, but it must have a method here called calibrate, and that's things here. What is this method doing? Determine the calibration type and you execute the corresponding method, right? How is that determined? By the calibration type. What's the calibration type? It's a toggle interaction collection, and you have here this switch case statement that you decide what kind of calibration. You have location based, which is the default one. You have fixed point calibration, spatial anchors calibration. All those calibration types are described in the paper, but let's stick here for the default cases. Calibration, location based calibration. You go back there and show where is this calibration type is defined. Here, calibration type, right? If you go to the calibration manager here, you have the calibration type, and this ratio collection calibration type is defined here in the calibration menu, which is hidden, but you can open here for a while and check. So you have here this radio button menu where you can select the calibration type, and the default one is the location based calibration. If you select fixed point, you do the calibration as a fixed points and the spatial anchors, but that is maybe is a topic for another tutorial. Let's stick here to the calibration basic. And okay, so we have here a function calibrate, and then they will start the calibration using the GPS, which is the location based one. And here is the function, and then here is all the script to create the calibration spheres. So we have 4 spheres. You define where the position, defined by the square length, and those are created. And then once those calibration spheres are created, the user can start collecting points. All right. And then, okay, the next thing that I want to show you, take this opportunity, is, and then you're gonna come back here later, but let me show you something. You have as well this script here that's called calibration sphere script. What is this calibration sphere? The script. This is a script that's associated to the calibration sphere that detects with the camera the user collides with the sphere, and once it collides and stay there for a while, it starts collecting points, right? So the code here is commented so that you can understand, but the idea is may start making requests for the Geo for HoloLens application to collect points so that you can have the control points to do the calibration. Where are those calibration spheres? Have here prefabs. This is the calibration sphere, and they have this script associated. Okay, and then when you click their location, let's go back to the calibration manager. When you click there, you have the 4 calibration spheres, and they will be listening for waiting for the user to collide them and to collect the points. And once all 4 points are collected, once all 4 points are collected, the spheres, after the fourth sphere is collected, then you call the calibration manager the set transformation. Right? It's here when only when have collect the points for all 4 spheres, they're gonna call this function set transformation. And basically here you have this flag in case you click on this checkbox, choose fake coordinates for indoor debugging. That is gonna be generated. Generate fake coordinates. You can have the code, have a look on the code later, but that's not the aim. But here you're gonna initialize and calculate the Helmholtz transformation. It means I'm gonna use the location of the user, the local coordinates together with the collected GPS points to calculate the the parameters, right? Oops, no, it's not this here. Set transformation. You can here initialize Augmented transformation. So they're gonna start. So we have the target points, which are the local coordinates, and you have the source point, which are the collected GPS, and they're gonna here use the helmet transformation, which is a class provided by the spatial transformer DLL to prepare this transformation, and finally calculate the parameters, and then you can calculate the accuracy, and you can even create the accuracy spheres. And then once you have those parameters calculated, you can load the geoscene, right? This is the basic functionality. So alright, this is about the location-based calibration. In another tutorial I will explain the fixed point calibration. Okay, so then let's go back here to our application. I will simulate the calibration here. In another tutorial I will do execute this program using the HoloLens after the deployment. So I'm running here the application. Let's once again do the indoor debugging, and you have here the parameters calculated. It provides the vertical and the horizontal accuracy. So once you have this calculated, you can click on the button here, load geoscene, and then you load the features. Let's have a look on this button here, load geoscene, button load geoscene, and you can once again you can check here what is doing here. You have set of things happening with the user interface. So once you load it, click this button, you have this scene, the user interface handle. You basically deactivate and activate objects using this scene handle, which has this script here. It's basically a script to hide and show the game objects, nothing else, right? But the main function that is run here when you click is visualization manager load geoscene. So we have here this game object visualization manager is empty object, but has this component script visualization manager. Let's open this script, and then here load geoscene. First thing, when you click there, it destroys all other georeference objects that you have there. And check first if the helmet transformation is calculated, because in order to display those georeference objects you need first to have the parameters, and if it exists you have all the information here to transform the coordinates, right? And then they're gonna tell how we want to load this geosync. The default case here is gonna load from the file. Which options you have here? The first case you want to load from the file, and you don't want to use the height relative, you want to use the absolute height to display, so where it's gonna be placed on the ground. But you can tell the height relative to the calibration and provide this information here, and this to load it from the file. And there is an option here to load from a server, which you are providing the functions, but of course you're not providing the web service, so you need to implement that yourselves. But all the asynchronous requests, HTTP requests are here. You just need to update the URL. But if you want to load from the file, which is the case that we are doing here, you have here the function load landmarks column, which are those cuboids here, digital landmarks from the file. You need to have the file name correct, which was scene1, and they're gonna load it from the resource folder, and you're gonna parse those GML file as a list of landmarks, this column, right? Parse GML. This is basically a class used to read XML files and construct this list of landmark column. What is this landmark column? Those are these digital landmarks. So they have a name, they have a height, they have a location, they have a side length, the height, the same information that they have there. What's the coordinate systems? And basically, sorry, there is someone knocking the door here, but continue. Sorry for that. And then you have all these informations. It's just like the plain old object here, right? And then you read this. Let's go back here. You read the GML file and construct a list of landmarks. That's the first thing. Load from file. And then once you have the list of these landmarks, you can create the landmarks game objects. What you're doing here, you're gonna take the list of landmarks, and one by one we will transform the coordinates using the parameters from the helmet transformation. First we need to do this. If you have using geographic coordinates, you need to transform to a project coordinate, because the parameters are from a project coordinate system to the local coordinate system. Please read the paper so that you can understand. That's very well explained there. And then here there is this flag that tells if you want to use the heights, if it's relative to the calibration, or you're gonna use the absolute height. You have these two options because sometimes it's not always easy to get the height, the correct height of the objects that you're highlighting, and then you can just maybe use the relative one to compare to where you are doing the calibration. And then you can instantiate those columns, these digital landmarks, using the transforming the coordinates, right? Using the helmet transformation. and they're gonna be handled, right? And then create the game objects in this function here. Well, this is the basic explanation. So let's go quickly here from the other scripts. So calibration manager, I already explained a little bit, but in a second opportunity I'll explain the fixed point calibration. You have the calibration sphere script that is responsible to detect if a user enters a calibration spheres and collect the points. Follow camera scripts. This is just a script that's associated to this camera collider. It's basically the collider that is required when the user enters the calibration spheres to detect if they collide with the calibration sphere. So there's nothing very important. Here is game object finder. It's used to find objects. I will explain that soon as well. And then here have a script about to manage the spatial anchors. That's explained in the paper as well. That's for the geo-anchor spheres. Here is scripts to manage the geospatial anchors. That's managed by the Azure portal from Microsoft. So here is implemented to use this cloud service from Microsoft. As long as they provide the service, you can use it as well, but it's required to have your own web server to store the anchors ID. I will explain that in another tutorial as well. Here is the plain old object class for the digital landmarks. I already show you. This is just to prompt the logs in this debug log menu that I show you in the previous. The first GML is already explained. The same UI handler is just to toggle or deactivate and activate objects, make them visible or invisible. So when you click the menus, which menu should be should be activated or deactivated. Slider text update is just in these sliders where you can just when you move the slider to update the text there so that you can visualize the value that's set. And here is the visualization manager. We already showed the script. And here, those are the assemblies, the DLLs that are used for our APIs. So you have here the the converter of coordinate systems. That's explained in the paper. You have as well your spatial transformer API, and the other one is the position collector that are explained there in the architecture. The other ones are dependencies from the spatial transformers. This Geo API and the Prognet that manage those transformations. What else? Yes, exactly. So if you have here the architecture, you're gonna see those DLLs here, and then everything explained in the paper, the calibration manager, the visualization manager, and how you load the GeoObjects either from the server or from the internal file. That's it. So in the next tutorial I will show you how to, this was just the basic about the code. In the next tutorial I will show you how to deploy this application to the HoloLens and to how to test it indoors, and in another one you're gonna make a test outdoors on how to use this application. So thank you very much. Hope this was useful.